In this video, I introduce restricted Boltzmann machines. Restricted Boltzmann machine is a Markov random field that consists of one hidden layer and one visible layer. The connections only between the hidden layer and the visible layer, but no connections between units in the same layer. The hidden units capture dependencies between the visible variables in the visible layer and generate new samples from the visible layer. The joint probability distribution is given by Boltzmann distribution, where Z is a partition function and E is the energy function. The first term is the edge energy between units I and J. The last two terms are unit energy. No connections between hidden variables makes the marginal distribution P of the visible variables over hidden state H easy to calculate. Namely, the marginal distribution is equal to margin of the joint probability over H. Using the definition of partition function after a few steps, we can express this marginal distribution as a product of multiple exports. RBM can be viewed as a neural network because the conditional probability of a single variable being on can be expressed as a sigmoid function, which is interpreted as a firing rate of a neuron. Since units inside one layer have no connections, Gibbs sampling can sample values at all units in one layer jointly. Given a simple training example V, using definitions of marginal distribution and the partition function, the log likelihood is expressed as a difference of two terms. Here, this summation over V and H is a partition function Z. Defining the log likelihood as an objective function, the gradient of the log likelihood with respect to model parameters theta can be expressed as two terms. I calculate the derivative with respect to theta, and then we have this summation of two terms to express the gradient of log likelihood with respect to theta. For the first term, if we let theta be Wij, we can simplify the first term as a sum of conditional probability times H times V. Using chain rule, we express this joint probability by product of conditional probability and probability P. And then we move this P out of the sum here because this P is not a function of H. Sampling method is used to compute gradients of log likelihood with respect to Wij, Bj, and Ci. From this step to this step, we use a small trick, namely when Hi is equal to 1, this sum of conditional probability over H is equal to this conditional probability. So we use the difference of two terms to express the gradient of log likelihood with respect to Wij. We sample this V over the data distribution, and we sample the second term over the model distribution. Similarly, we calculate the gradients of log likelihood with respect to Bj and Ci. Here is a pseudocode of computing gradient. First, for each training example, we give the input value to the initial value. And then in the forward pass, we update hidden state using the input data. And then in the backward path, we using the data using the hidden state to update the visible state. After key steps, we got this model distribution VK, and then now we substitute the VK to second term, and we use this V0 as a data distribution to update this delta Wij. Similarly, we update delta Bj and delta Ci until reach the convergence. For more details, please check with these references. Thank you. Bye.